So hello everyone and welcome to this next lecture in the DC-DC converter series, and we will continue with the simulation of a basic transformer. So this is where we had left off in the previous lecture, where we had calculated the two winding currents. So we had actually gone through the entire process. We had used the applied voltages across the windings to calculate the induced EMF, calculated the flux linkages, and used the flux linkages to calculate the currents. Now we will continue to actually create voltage sources so as to produce these currents. So as always, before I start this lecture, a little bit of background that if you are interested in these kind of video lectures but you would like something a little more comprehensive, I do have a full-length online course on the MOOC website Udemy. So this is the very first course, which is simulating power electronic circuits using Python. In this course, I talk about the basics of Python power electronics, how to install the software, some basic power electronics, and finally a case study on simulating a buck converter. If you are interested, on the other hand, more on the signal processing and control side, I have another course which is basics of digital signal processing for power engineers, and this is related to how you can design filters for power electronic applications digitally. So in this I talk about some basics of signal processing. I talk about how we can design and implement filters using Python, and finally there is a case study of designing a low pass filter and a notch filter using Python with frequency response characteristics. And my latest course, which is probably the most relevant for these last few lectures, is the simulation of magnetics for power electronics using Python. And in this I talk about how you can simulate magnetic components such as inductors, coupled inductors, and transformers for power electronic applications. And there is finally a case study of how to simulate a flyback converter, right? So this last course will be very relevant for the next few lectures that I'm talking about. So if you do want details of simulating transformers, you could check out this course. So with this background, let me go back to the lecture. So once again, let me go back to the circuit, and here let's talk about what we're going to do. We have a control voltage source and a variable resistor to represent a particular winding. So this is one winding. Now we have a two winding transformer, so we have two such voltage sources in series with resistances. Now the idea behind this is that we can control this control voltage source and of course also the variable resistor in such a way to produce a certain current. That current is dependent on the voltages that are applied to the two windings, right? That's how a transformer behaves. Transformer, you apply voltage on one or both windings, right? Anything is possible, and according to that a current will flow through it, right? So depending on how it is, for example, if a voltage is applied to the primary winding and a load is connected to the secondary winding, the applied voltage on the primary will set up an induced EMF in the winding, which will induce an EMF in the secondary winding, due to which a voltage will be made available to the load, and that in turn will produce a current. But in the end, what we do have is a voltage fed current source, right? We measure the voltage, we produce a current, and we've already done this in code. We have already measured the voltage and produced a current. Now the last step is to create this into a current source. So for that, let me go over to the simulator and talk about how we're going to do that. In the control output section for this same control file, that is the transformer model, we have outputs which are the control voltage sources and the variable resistors, right? Now we've given them values. Now these variable tags are all random values. That is, initially there is a voltage of 0 and there is a variable resistance is a value of 100. Now what we have to do is we have to now calculate these in the control code. So what I'm going to do, I'm going to copy all this and paste it here. So let me just paste it. It's always best to copy it from here so that there are no typos. And let me copy the other two as well. with this, we have now brought these outputs into the control file. So there are several approaches possible. You can keep the voltage constant, change the resistance, or you can keep the resistance constant and change the voltage, or you can change both, right? For simple cases such as this, I would suggest that we keep the resistance constant and change the voltage. So now the question is, if we keep the resistance constant, let's move it to the head of the file where we have all this. So this is where we move, and we'll place it here. Let's get rid of these indents. So now the question is, what should be this resistance winding 1? Now this resistance winding 1 has no real implication, right? This is an internal resistance to this model. It can be anything. However, when we do choose it, it's important that we take into account that the value of this resistor can have an impact on the stability of the simulation. Therefore, what I would suggest is, let us match this variable resistor to the impedance of the system. And the impedance of the system is the rated impedance that we have already calculated, right? So if we go here, you will see that we have I1 rated and V rated. So these two will produce a rated impedance. This is the rated impedance of the system. And I would suggest that we just keep it at the rated impedance. So what I would say is, let's just copy this and paste it here, and let us copy this and paste it here. So this is just a random value that I'm placing. You could assign it a value, like I could make this 100. Instead of this, I could just make it 100, right? That's perfectly okay. But the reason why this calculation is better is because as your system changes, your rated impedance of your system will also change. For a higher voltage system, you might have a slightly higher impedance. Similarly, for a lower voltage system, you would have a lower impedance. So rather than actually taking some random value, which may not reflect on the condition of the system, it is better to actually assign the rated impedance of the system to this resistance so that it is always matching with the rated impedance of the system. So now that we have this, we just have to now calculate this source voltage, voltage source for the two controllable sources. So now the question is, what direction do we take? Let's look at this induced EMF. The induced EMF is equal to the voltage or applied voltage minus the resistive drop. So let's go back here and let's look at this. Let's assume that this is a voltage, applied voltage, and this is our induced EMF, right? And there is some internal resistance. For the induced EMF to be equal to the voltage minus the resistive drop, this current has to be flowing into the winding, right? And the same for this as well. This is just simple Kirchhoff's voltage law. If you have a doubt, just go and draw the circuit and write this equation yourself. It's just simple Kirchhoff's voltage law, where V minus IR is equal to E. And for that to happen, this current has to be flowing downwards. Now, if the current has to be flowing downwards, this controllable voltage source will have to be equal to the induced EMF, right? Let's take a look at this. So now, for example, if this we have already calculated the current. We have the applied voltage. We now have to generate a voltage source that's such that this current will flow, and this is with respect to the applied voltage. So therefore now it's the same equation. V voltage minus the drop across, now not the internal resistance but this external resistance. This drop across external resistance has to be equal to the voltage source, right? That's how it is. So all we have to do is we just have to come here and replicate this equation. So only thing, let me just copy this and paste it here. Only difference is the resistance will now be the resistance of the winding that we've chosen. This is the variable resistance. that is this variable resistance, right? So let's go back here and let us copy this for the second one as well. And this will be equal to winding 2, current 2, resistance 2, right? So this completes our transformer model. Alright, it was a long one, took several lectures. Now, before we actually start analyzing, I would say, let me go and run this simulation. So view the output and let's click on run, because it's always possible that there may be a small bug, particularly when you have controls. As always, when you run a control file, always go and check the command line and you see there is an error, and this is what I was expecting, that there would be some error. So let me go and see what's happening. Now the error is the local variable psi1 reference before assignment. Now let's see what's happening. This psi1 is the flux linkage, and you see it is a plus equal to. This has a memory, so therefore we need to define this as a static variable. Now let me go and see if that has been done. And we do not have it as a static variable. That is the problem. So let's go and add it. Let me go back. Let me copy this and paste it here. Let me save the static variable. Let me go back. Go back to the code, copy the second variable and paste it here. So let's go and try running it again. Click on the run button, and this time the simulation is running. So we have now passed the first hurdle, that we now have a simulation which is running successfully. The next step is we need to analyze the results. As before, I would like to stop this lecture to make sure the lectures don't get too long. So therefore, we will continue with the analysis in the next video, which will be next week. So as before, if you have any doubts about what I did, and it is quite possible, one option is please do watch some of these videos again, because I do understand some of this might be a little complicated. And if you need more details, please do check out this course, which has details of this, of all the details of this transformer, right? Of how to simulate transformers, basics of transformer theory, and also detailed coding lectures, right? So if you have any other doubts, feel free to post in the comments or email me or send me a message on social media, whichever is your preference. Otherwise, I will see you next week, where we will add the plots and analyze the waveforms. So thank you so much for listening, and goodbye for now. See you next week.